Hello everyone, I'm glad to have the opportunity to report our research. The title is A Novel Robust Zero-Watermarking Algorithm for Medical Imagers. I will show my presentation in the following aspects. It includes an introduction, algorithm details, experimental results, and conclusion. Well, let me introduce the background of this paper. We divided the medical image watermarking algorithms into three classes. The robust medical image watermarking algorithms focus on the robustness of algorithms. Those algorithms aim to control the balance of robustness and imperceptibility by using some common optimization algorithms. The zero-watermarking algorithm is very popular due to its ability to copyright protect medical images without altering them. However, the robustness of this type of algorithm is generally low. Medical image watermarking algorithms with tamper detection capabilities enable the protection of image copyrights, while having the ability to detect the image tampering. However, the location and the shape of the detection region are obvious, and there is a large gap with the article situation. Traditional watermarking algorithms provide copyright protection by embedding watermarks into the host image, which may bring the three main problems for medical images. First, inserting information into the host image modifies the original host image, which may cause a doctor's misdiagnosis due to any content modification. Second, the insert schedule causes the traditional watermarking algorithms hard to balance the robustness and the imperceptibility. Third, very few watermarking algorithms consider copyright protection and tampering detection simultaneously. To overcome the problems, a robust and efficient image watermarking algorithm where EMD and dimensionality reduction is developed. The motivation of our research is like this. First, protect the copyright of medical images without any content change of the involved images. Second, detect whether the medical images are tampered or not. Also precisely locate the position of tampering region. Third, exhibit good robustness for copyright protection and tampering detection against the viral attacks. Let's move on to the algorithm details of our work. BEMD is also achieved by the shifting processing, which involves the main steps of local extreme extraction, envelope computation, and the stopping criteria of the shifting. Figure 1 shows the decomposition result by BEMD. Each MF component represents an intrinsicity model function that exists in the original image. Usually, the leading MFs contain the high-frequency details of image, and the residual contains the low-frequency information of the image, reflecting the overview shape of the image. The multi-scale decomposition of BEMD makes our algorithm can detect tampering and protect the copyright of medical images at the same time. Therefore, BEMD is adopted in our zero-watermarking algorithm. The Arnold transform algorithm is simple, periodic, and will get the original image again when it iterates to a certain step, which is widely used in image scribbling. Figure 2 shows the watermark image and the result after Arnold transform respectively. After 8 transformations, it can return to the original state. Figure 3 illustrates the overview of the newly proposed algorithm by taking the scale as the host image and the elephant as the watermark image. For the host image, Figure 3a It is first decomposed into the multi-scale representation of IMFs and a residue by BEMD, figure 3b. Then, the first IMF and the residue are decomposed by SVD. The larger value in the upper left corner of the single matrix S is selected to reconstruct the matrix figure 3c. After that, both of the matrices are performed by binary option, figure 3d. At the same time, the watermark image is encrypted and repeat encrypted image to the same size as the host image, figure 3g. Finally, the feature image, figure 3i, is obtained by performing an XOR option. Given the similarity between tamper detection and robust feature image construction, the algorithm on the left shows only the construction process of the tampered feature image on MF1. The zero-watermarking embedding algorithm first performs the BEMD on the host image, and the first IMF obtained is decomposed by SVD. Then, the coefficient matrix is binarized using equation 2. On the other hand, the watermark image is encrypted by Arnold transform and repeated to the same size as the host image. Finally, the watermark image is subjected to an XOR option with the host image, and the obtained feature image is saved to the copyright authentication center. Figure 4 illustrates the process algorithm for watermark extraction and tamper detection in this paper. First, the tampered image is subjected to the same options as in figure 3, BEMD, SVD, and binarization. Then, the image saved in the copyright authentication center is subjected to the XOR option with the first layer of IMF and the residue respectively. The image obtained in IMF1 is extracted by the voting strategy to extract the robust watermark image. The extracted watermark image can be used for tampering detection in the template for detection. Figure 5 shows the original host image and the detection result after tampering with 2 blocks. Grids are numbered from top to bottom, from left to right. Both tamped blocks are detected and identified using the rate numbers. As shown in figure 5, the area involved in the red number is successfully detected, and the specific location can be accurately located. Now, let me show some of our results. The NC values of recovered watermarks are tabulated in Table 1, from which we can see that NC values of the extracted watermark images are 1 under 12 kinds of attacks, including filtering attacks, noise attacks, and image enhancement attacks. 8 medical images are subjected to 3 kinds of random tampering. Despite the complexity of tampering reasons, some of which contain multiple blocks, the algorithm can still successfully detect it with a success rate of 95.84%. The result in Figure 5 shows that the algorithm in this paper can detect it and locate tampering reasons for a single small block and multiple blocks. From Figure 6, the highest success rate is 96.36%, and all the success rates are larger than 92%, which illustrates the proposed algorithm performance well in tampering detection. From Figure 7, we can observe that our method is better than the other 3 algorithms. Algorithm 20 is no blind watermarking algorithm by combining BEMD, DWT, and LWT. During the embedding and extraction process, the BEMD is performed 3 times. For the downsampling scale of DWT is adopted, algorithm 20 is faster than the algorithm 21. When the size of the original image is 1024, the time is about 97 seconds of algorithm 20, and our algorithm takes only 47 seconds. This shows that our algorithm is very efficient. The left subfigure shown in Figure 8 gives the comparison results with algorithm 23 and ghost noise attacks. Both our algorithm and algorithm 23 are able to achieve the NC equal 1 at a lower intensity of 1% ghost noise. As for cropping attacks, after 20% cropping intensity, our algorithm clearly outperforms algorithm 23, achieving an NC value of 0.95 at a maximal cropping intensity 56%. The comparison result shows that our algorithm has a strong ability to resist the ghost noise attacks and the cropping attacks very well. In order to evaluate the efficiency and advantage of the proposed watermarking algorithm, we compared our algorithm with 6 robust medical image watermarking algorithms. From Table 2, we can see that our proposed algorithm has a good resistance to ghost noise, GPEZ compression, median filtering than other compared algorithms. 3 medical image watermarking algorithms are used for the comparison of tampering detection. As shown in Table 3, the algorithm proposed in this paper significantly outperforms the result of the other 3 algorithms on no attack, median filtering 3, paper and salt noise, ghost filtering, sharpening attack, GPEZ compression, and histogram equalization attack. From Table 4, we can see that our proposed algorithm outperforms the other 3 algorithms and 8 attacks, which also indicates that the proposed algorithm has better robustness on no medical images. Finally, our paper can be summarized as follows. A large number of experimental results and comparison with previous algorithms has confirmed that our method can detect the image tampering and efficiently protect the properly rise of medical images. Our newly proposed zero-watermarking algorithm not only has stronger robustness against viral attacks, our new algorithm also has great processing and analysis potential in natural images. Thank you for your attention. That's all.